To convert this integral into the sigma notation with an infinite limit, we need to first establish what the dx is. Okay, so the dx part of this is going to be the interval width. In this case, the interval width is going to be found from the bounds of 0 and 2. And so we take the interval width of 2 and divide it by n. And that's going to be our dx part of this expression. The other part that we need is the x part of the expression. That x part we can find by taking the interval width, which is 2, and having it as k over n. So putting this into the sigma notation, we can do this, the limit as n approaches infinity. We're going to start at k equals 1. For when k equals 1, when we plug this all in, we're going to end up with 0. So we're going to start at 0. And then we are going to end at k equals infinity. Or sorry, I'm going to write that as n, which is infinity. So k equals 1 to n. And the expression then is going to be, well, we have our e part of that. Okay, we have 2 times the x portion of that is going to be reflected by the 2k over n. Okay, so that reflects the x part of that expression, and then we need to multiply that by the dx. Well, the dx is going to be the interval 2 over n. Okay, so that represents our dx part. So this then is the sigma notation for this expression. So we can simplify this a little bit. The limit as n goes to infinity. We're going to start from a k value of 1 to infinity, e to the power of 4k over n. And that's going to be times by 2 over n. And again, that reflects my dx, this portion here. And we can test this. We can plug in k equals 1 and n equals infinity, and we get e to the power 0. Okay, so we're going to start at, 2 times 0. So we're going to start at 0, and then e to the power, when we plug in k is infinity, n is infinity, we're going to end up with the x value in here. That's going to be equal to 2, so those are the correct bounds that we have on the integral that was given. This last problem, it says for a continuous function, f, the right Riemann sum approximation of the integral from 0 to 2 of f of x dx with n subintervals is given by the expression 2 times n plus 1, 2 times n plus 1 times 3n plus 2 in brackets, all over n squared. And so what is the value of that integral from 0 to 2? Well, we don't need to generate the Riemann sum because really we want an infinite interval, infinite value of n, which really just means that we're going to take a limit of this expression that we were given. If we take the limit of this expression as n goes to infinity, that is the same as the integral. Okay, so we're going to say this. So the limit as n approaches infinity of the sigma form, that's going to generate my integral form. Okay, so we're trying to evaluate this integral, and we can do that by actually taking the limit here. So we're going to then say that the limit as n approaches infinity of that expression, 2 bracket n plus 1, 3n plus 2, over n squared. Well, as I do the limit for this, we end up with a quadratic in the numerator with coefficient of 6. We have a quadratic in the denominator, so this is going to have a limit of 6. So what that means then is we could take that limit value and say that that then must reflect the integral value because that's our limit as n goes to infinity. So the answer to this then is the area under the curve from 0 to 2 of whatever this function f of x is, that's equal to 6. And so we don't need to go and convert this notation into that notation with n into an f of x function, because we can just take the fact that the limit of that notation, of the n notation, is going to give us the area under that, the exact area under that integral.